Let's do the proof for the formula that the partial pressure of, let's say, for example, gas A, partial pressure for gas A, that's going to be equal to the mole fraction for particle A times the total amount of pressure there is. Now we know that in a container, if there was many different types of gases, the total amount of pressure would be equal to the pressure exerted by particle A. So let's say if the purple particles were particle A, all of these purple particles would be exerting some sort of pressure on the container. Same with the green particles, right? All of these will be exerting a pressure as well, and so will the white ones. So the pressure, let's just say, exerted from the purple particles plus the pressure exerted from the green particles plus the pressure exerted from the white particles is going to give us the total amount of pressure, right? Because, yeah, if you just add up all the partial pressures, you get the total amount of pressure there is. What's another way to represent pressure? Well, you can use it using the ideal gas law. PV equals nRT. If you divide both sides by V, you get that the pressure is going to be equal to nRT divided by V. Notice how, if we're assuming that all these gases are in the same container, notice how the volume for all of these gases, that's going to be the same when you're using the ideal gas law. Notice how the temperature is also going to be the same, right? Because it's the same container, right? It's same set of conditions, right? This is a constant, the ideal gas constant. So the only thing that could change is the amount of moles of gas you have, right? In this diagram, notice how there's 4 purple particles. There's there's 4 white particles. I don't know why I said 3. And then there's 5 green particles. So the amount of moles of gas you have can change, but everything else pretty much stays constant, right? At this side of the equation. So if I actually substitute nRT over V for P, right? If I just substitute this in for every single one of these pressures, I'm going to get nRT. Actually, let me do this. NA RT over V plus NV and B RT over V plus NC RT over V, and then this goes on forever. Right? Notice how the only thing that changes is the amount of moles of gas we have, right? In this case, we have N moles of gas A, N moles of gas B, N moles of gas C, right? We don't know how many moles of gas A, B, or C we have, but we do know that it's like it can change, right? It doesn't have to be the same, right? We know that all these other variables are constant, but we do know that this moles of A and moles of B, they can change, they can be different. So that's why I use this A, B, and C to represent that these values could be different from each other, right? Now, what I'm actually going to do is I can factor this. Now, if we factor this, we're going to get P total. That's going to be equal to, now, this is what you get after you factor all of these terms, right? Notice how when you distribute this RT over B back into these terms, you get exactly what you had originally, right? So that's how you can check that these two things are equal, right? It's just going to be the sum of all the moles of gas A plus B plus C, dot, 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 because there could be more gases. And then after that, it's going to be all multiplied by RT over V because that's constant. Now, recall that, well, if you add all the moles of gas together, that's going to be equal to the total amount of moles of gas you have, right? So for this Na plus N, the moles of B plus this moles of C, right, that's going to add up all the way to the total amount of moles that you have. So I could just substitute that in here. So the total pressure is going to be equal to the total amount of moles multiplied by RT over V. Now, what I'm going to do is I'm actually going to multiply both sides by the mole fraction. Recall that the mole fraction of a specific gas, let's just say gas A, that's going to be equal to the moles of A that you have, divided by the total amount of moles there are. Aka N total. What I'm going to do now is I'm going to multiply both sides of this equation by the mole fraction. So I'm going to get the mole fraction. Actually, let me do this. The partial pressure, not the partial pressure, the total pressure multiplied by the mole fraction, that's going to be equal to N total RT over V, multiplied by the mole fraction. We also said that mole fraction is equal to moles of A over N total, so let's actually just write that out. So moles of A, aka Na, right? The moles of A over the total amount of moles there are, N total. Notice how when you write all of this out, the N's cancel out, the N totals cancel out. So you're just going to be left with P total times the mole fraction. That's going to be equal to, and then N moles of A, and then RT over V. However, we did recall that, remember when you're doing P equals NP, V equals nRT, when you divided both sides by P, you get that P is equal to nRT divided by V. So in this case, guess what I have? nRT divided by V. And because I'm using moles of A, all of this right over here is going to be equal to P, the pressure for A, gas A, right? Because if we have N moles of A, that's going to lead to the pressure for A, right? So PA is going to be equal to P total times the mole fraction. And that's our proof. That is our proof. Yep. All right. Nice.